Uranus is the only planet in the solar system that rotates on its side. Its axis is tilted 98 degrees, not slightly, not a bit off-center. It is essentially lying down. It rolls around the sun like a bowling ball, its poles pointing roughly toward the sun instead of perpendicular to it. Something hit Uranus, something enormous, and the impact was violent enough to permanently knock the entire planet over. We've known about the tilt for centuries. What we've been arguing about, and what a 2023 computer simulation finally shed new light on, is exactly what hit it, and whether that collision also explains the other mysteries. Because Uranus has a lot of mysteries. It is colder than Neptune, despite being closer to the sun. Its magnetic field points in the wrong direction, at the wrong angle, from the wrong place. It has rings that nobody expected, and moons that, as of 2023, appear to have active subsurface oceans that nobody predicted. Uranus is the most scientifically neglected planet in our solar system. One spacecraft, one flyby, 6 hours, in 1986. Everything we know about Uranus comes from 6 hours of data collected 40 years ago. And it's already full of things we can't explain. Let's fix that. In January 1986, the Voyager 2 spacecraft flew past Uranus. It was the only spacecraft that ever has. It spent 6 hours in the Uranian system, flying past a pale blue-green sphere at 64,000 kilometers per hour, its instruments scanning frantically, collecting everything they could in the brief window of close approach. Then it kept going, toward Neptune, toward interstellar space. That was 40 years ago. In the 4 decades since, no other spacecraft has visited Uranus. No orbiter, no probe, no lander, nothing. Every other planet in the solar system has received multiple missions since 1986. Mars has had rovers, landers, orbiters, and helicopters. Jupiter has had Galileo and Juno. Saturn had Cassini for 13 years. Even tiny Pluto got a flyby in 2015. Uranus has had 6 hours. And in those 6 hours, and in the decades of Earth-based observation and computer modeling that followed, we found a world so strange, so anomalous, so full of contradictions that planetary scientists have been arguing about it ever since. It rotates on its side. It's colder than it should be. Its magnetic field makes no sense. It has rings nobody expected. And as of 2023, its moons may be hiding oceans. Uranus is not a boring, featureless ice ball that deserves its place at the back of the solar system family photo. It is the most misunderstood planet we have, and we are long overdue for a proper introduction. Let's start with a classification problem. Uranus is almost always grouped with Jupiter and Saturn as a gas giant. It isn't one. Uranus, along with Neptune, belongs to a separate category, ice giants. And the difference matters enormously. Jupiter and Saturn are predominantly hydrogen and helium. Their interiors are dense, hot, and metallic. Their atmospheres grade smoothly into their interiors. Uranus is different. Its bulk composition is dominated by what planetary scientists call ices. Not frozen water alone, but a mixture of water, ammonia, and methane in a hot, dense, supercritical fluid state. Not actually frozen. The word ice here refers to the chemical composition, not the physical state. This fluid, hot, pressurized, electrically conducting in places, makes up the vast majority of Uranus's interior, below a relatively thin hydrogen-helium atmosphere, above a small rocky core. The atmosphere itself is what gives Uranus its color. Methane in the upper atmosphere absorbs red light and reflects blue and green wavelengths. The result is that unmistakable pale cyan teal color, one of the most distinctive in the solar system. But here's what most people don't know about Uranus's appearance. It's almost completely featureless. When Voyager 2 flew past, it photographed a smooth, nearly banded, structureless sphere. Where Jupiter has violent storms and Saturn has subtle bands and the hexagon, Uranus presented what appeared to be a blank canvas. Scientists nicknamed it the bowling ball. That apparent featurelessness is itself a mystery. Neptune, almost identical in composition and size, has visible storms, dark spots, and dynamic atmospheric activity. Why does Uranus look dead when Neptune looks alive? The answer connects directly to the strangest fact about Uranus, the one that makes it unique in the entire solar system: its internal heat. Uranus's axial tilt of 98 degrees is not natural. No planet forms tilted like that. The protoplanetary disk from which planets form is flat. Planets form rotating upright or close to it. Small tilts can develop over time through gravitational interactions. But 98 degrees, something hit it. The question has always been, what exactly? And when? For decades, the leading hypothesis was a single massive impact. One large protoplanet, roughly Earth-sized or larger, slamming into the young Uranus billions of years ago with enough momentum to tilt its entire rotation axis. Simple, clean, explains the tilt, but it creates a problem. If a single massive impactor hit Uranus and transferred that much angular momentum, the collision would also have generated enormous heat. Heat that should have persisted for billions of years. Heat that Uranus should still be radiating today. But Uranus radiates almost no heat. Its internal temperature is nearly the same as its surface temperature. The heat that should be there isn't. A 2018 study proposed a solution. The impactor wasn't a single rocky body. It was an ice-rich body, a large protoplanet or planetesimal composed largely of ices that hit at a relatively low velocity and a glancing angle. A slow, icy, sideways hit. That kind of impact could tilt the axis without generating the same catastrophic heat surge. The ice-rich impactor would have mixed into Uranus's interior, potentially creating a thermal barrier, a layer that traps the planet's internal heat and prevents it from radiating outward. Effectively, the collision that knocked Uranus over also insulated it, buried its heat under a chemical blanket, and a 2023 computer simulation went further. It modeled the collision in unprecedented detail and found that a single impactor may not be enough. The current distribution of Uranus's moons, their tilts, their orbits, their composition, is best explained by a series of smaller impacts rather than one giant one. Multiple collisions, a violent early history, each one adding to the tilt, reshaping the moon system, adding to the thermal insulation. Uranus didn't have one bad day, it had many, and it has never recovered. Here is something that should not be true. Uranus is the coldest planet in the solar system, not Neptune. Uranus. Neptune is almost 1 billion kilometers further from the Sun than Uranus. By every reasonable calculation, it should be the colder of the two. It isn't. Neptune's minimum atmospheric temperature, -218 degrees Celsius. Uranus's minimum atmospheric temperature, -224 degrees Celsius. Uranus, the closer planet, is colder. Every other planet in the solar system radiates more heat than it receives from the Sun. Their interiors are warm, remnants of the heat generated during their formation, or produced by radioactive decay, or generated by gravitational compression. That internal heat leaks outward and warms the atmosphere. Jupiter radiates 1.7 times more energy than it receives from the Sun. Saturn radiates 1.8 times more. Neptune radiates 2.6 times more. Uranus radiates essentially the same energy it receives. Its internal heat output is close to zero. Something is blocking it. The leading explanation connects directly to the collision. The impact that tilted Uranus, particularly if it involved an ice-rich body mixing into the interior, may have created a stable layered structure inside the planet. A thermal stratification, a chemical boundary layer that acts like insulation, trapping the internal heat and preventing it from reaching the surface. Think of it like a thermos flask. The heat is in there, it just can't get out. If this is correct, the interior of Uranus may be significantly warmer than we can measure from outside. The internal heat that should have dissipated over 4.5 billion years is still trapped, still locked inside, which means Uranus is not a cold, dead world. It's a world with a fever it can't break. And that trapped heat changes how we think about everything inside it, including the diamonds. Every planet with a magnetic field generates it the same basic way. A conducting fluid, molten iron, metallic hydrogen, circulating in the interior. The circulation creates electrical currents. The electrical currents generate a magnetic field. The magnetic field is roughly aligned with the planet's rotation axis. Roughly, Earth's magnetic pole is about 11 degrees off from its geographic pole. Jupiter's is about 10 degrees. Saturn's is almost perfectly aligned. Uranus's magnetic field is offset from its rotation axis by 59 degrees. That's not a small misalignment. That's a completely different geometry. The magnetic north pole of Uranus is not near either geographic pole. It's somewhere in the middle latitudes. But it gets stranger. The magnetic field doesn't even originate from the center of the planet. It's offset from the planet's center by about 1/3 of the planet's radius. Off-center, asymmetric, pointing sideways relative to where it should be. The result: Uranus has the most chaotic, lopsided, asymmetric magnetic field of any planet in the solar system. As the planet rotates, the magnetic field wobbles wildly. Its strength varies enormously depending on where you are on the planet's surface, by a factor of up to 10 between the weakest and strongest points. Why? Almost certainly because the magnetic field isn't being generated in a metallic core, like Earth's, but in the electrically conducting icy fluid of the interior. Liquid water, ammonia, and methane under pressure can conduct electricity, and the chaotic convection patterns in that fluid create a chaotic magnetic field. Neptune has a similarly chaotic magnetic field, supporting the idea that this is a property of ice giants in general. And that same interior, the hot, pressurized, ice-rich fluid, is where something spectacular may be happening. Diamond rain. At depths of about 8,000 kilometers inside Uranus, where pressures reach millions of atmospheres and temperatures hit thousands of degrees, methane breaks down under the extreme conditions. Its carbon atoms separate from the hydrogen, and that carbon, under those pressures, crystallizes into diamonds. Diamonds form and sink through the fluid interior of Uranus, accumulating at depth, potentially forming a diamond layer around the core. Laboratory experiments at Lawrence Livermore National Laboratory have reproduced this process, firing lasers at plastic samples to simulate the conditions inside ice giants and watching diamond crystals form in real time. Uranus almost certainly contains diamonds, billions of tons of them, falling like snow through the interior of the most overlooked planet in the solar system. Uranus has 27 known moons, all named after characters from Shakespeare and Alexander Pope. Most of them are small, dark, unremarkable. Rocky bodies captured early in the solar system's history. But 5 of them, Miranda, Ariel, Umbriel, Titania, and Oberon, are large enough to be spherical, large enough to have undergone geological processing, large enough to potentially have interesting interiors. For decades, they were assumed to be cold and geologically dead. The Voyager 2 flyby showed heavily cratered, relatively featureless surfaces. Case closed. Boring moons. In 2023, a team of researchers reanalyzed Voyager 2's 40-year-old infrared data using modern analysis techniques that didn't exist when the data was first collected. What they found was not expected. 4 of the 5 large moons, Ariel, Umbriel, Titania, and Oberon, show thermal signatures consistent with active internal heat. Heat that can't be explained by radioactive decay alone. Heat that suggests something more dynamic is going on inside. The most likely explanation: subsurface oceans of liquid water. Maintained by tidal heating, the same mechanism that keeps Europa and Enceladus liquid, and possibly by the heat trapped in the moon's interiors. Ariel in particular shows surface features, fractures, smooth plains, resurfaced regions that on any other moon would immediately suggest cryovolcanism, material from a liquid interior erupting onto the surface and freezing. If Ariel has a subsurface ocean, then Uranus has not 1 but potentially 4 worlds with liquid water, 4 potential habitats for life, around a planet we visited for 6 hours 40 years ago and then ignored. This single 2023 reanalysis completely transformed the scientific case for a Uranus mission. Suddenly, Uranus isn't just a tilted curiosity. It's potentially the most life-rich system in the outer solar system. In April 2022, the National Academies of Sciences published the Planetary Science and Astrobiology Decadal Survey, the document that sets NASA's priorities for the next decade of planetary exploration. For the first time in history, the top priority flagship mission was not Mars. It was not Europa. It was Uranus. The Uranus Orbiter and Probe, UOP, was ranked as the single highest priority large mission for the coming decade, above everything else. The scientific case had become overwhelming: an ice giant with a dramatic tilt, a missing heat source, a chaotic magnetic field, potential diamond interiors, and up to 4 moons that may harbor subsurface liquid water. All of it understood from 6 hours of data collected 40 years ago with 1980s technology. The UOP mission concept involves an orbiter that would spend several years in the Uranian system. Not a flyby, but a true orbital mission, the equivalent of what Cassini did for Saturn, and an atmospheric probe that would plunge into Uranus's atmosphere and measure its composition directly. The atmospheric probe is particularly important. The composition of Uranus's interior, the ratio of water to ammonia to methane, the distribution of heavier elements, is fundamental to understanding how ice giants form. And we don't know it. We've never measured it directly. The launch window, if funding is approved, would open in the early 2030s. If launched then, the spacecraft would arrive at Uranus in the early 2040s. That's a long time, but consider what we'll learn. We'll finally know how thick the atmosphere is, how deep the cloud layers go, what the composition of the interior actually is, whether the magnetic field really is generated in the icy fluid layers, whether the moons have oceans, whether Ariel has cryovolcanism, and perhaps most importantly, we'll finally be able to compare an ice giant in detail to what we know about gas giants. Understanding the difference between Jupiter and Uranus is not just academic. Most exoplanets discovered so far fall into the size range between Earth and Neptune. Understanding how ice giants form and evolve is directly relevant to understanding the most common type of planet in the galaxy. Uranus isn't just a neglected corner of our solar system. It's a key to understanding the universe beyond it. We spent 40 years ignoring it. The next generation of scientists won't have to. Subscribe, hit the bell, and tell me in the comments, which of Uranus's moons do you think is most likely to have life? I'm going with Ariel, but I have been wrong before. Until the next mission.